Hello, and welcome to my presentation on experimenting with reinforcement learning through Waterworld. In the top right corner, we can see an example of Waterworld. We have the blue agents called pursuers chasing the green food and avoiding the red poison. And those little lines you can see out of them are how they see the world. Those are their sensors. As we can see from this diagram on the right-hand side, they can sense just about anything in the environment, and they are able to apply horizontal and vertical thrust in order to move about the world. So why do we want to work on this project? We want to develop RL models, and we want to experiment with different network architectures, and we want to attempt to increase the learning ability. We want to learn as well as possible how to develop a good agent. Why do we want to do this? It's both interesting and complex because of the continuous world that these agents live in, and it's also educative. It teaches us how to build agents and how to develop agents in such a way that they will work better in such a world. Now, as I was developing this project, I came across a pretty big problem. Here you can see several different agents with several different architectures that I've developed. We have Advantage Actor Critic in blue, we have DDPG in green, and a Q-learning neural network in red. I also have a purple, which is random, and an orange, which is a controls algorithm that I developed. As you can see, all of them do worse than the controls, and most of them do worse than the random. This is problematic because it means the agents aren't any better than developing just a simple algorithm in order to accomplish this goal. So in an attempt to increase the learning, better the learning of the agents, I came up with a couple of experiments. First of all, I experimented with different types of memory. We have the standard memory where it just selects an observation at random, and then I have my own type of memory called reward prioritized memory. On the right, we see an example of instantaneous rewards throughout an episode, and you can see there are several high peaks and a couple of low dips, but most of the observations are pretty linear. So my thought was, what if we prioritize the memories that actually yield some kind of reward, and the larger the reward, the more we will prioritize them. And so that's exactly what I did with reward prioritized memory. Rarer memories are more likely to be selected, and that is calculated through developing a Z-score for them. I also developed something I call the controls policy trainer. And the reason for this is the controls algorithm that I developed is fairly good. It pursues food fairly well and avoids poison fairly well. It's definitely not optimal, but it does fairly good. On the right here, we see an example of observations coming in through the episode. And you'll notice these spikes appear almost seemingly at random. But as you think about it, by understanding the observations, the closer to zero, the closer the food or poison is to the agent. That's pretty obvious towards us. We want to try to get the food closer to the agent. So my thought is through this controls policy trainer, this controls algorithm, we can train a policy for DDPG so that it can learn from the controls algorithm, kind of like imitation learning, and try to mimic it and then improve on it. So results. With the memory, I didn't see all that too interesting of results. You'll notice that these losses are on different scale. That's because each algorithm uses a different type of loss, so they're not fair to compare against each other. And honestly, the reward prioritized memory seems to be a little bit more stable, as in the peaks tend to be a little bit lower, but it doesn't really yield good results all around. Normal memory seems to do just as well, perhaps with the exception of DDPG. Where the reward prioritized memory does consistently get a lower loss, but I feel that's inconclusive and would need more experience. So in conclusion, the memory type does not seem to matter for this purpose. Controls policy trainer, on the other hand, we have a couple of graphs here. On the left, we have the reward. On the right, we have the loss, and you will notice there is an immediate dip in loss for the actor for the DDPG. And this is exactly what I was hoping for. A dip in loss, which means the actor is learning more quickly, and then hopefully we'll be able to start improving on the algorithm sooner. You'll also notice that the reward is more stable. It doesn't dip quite as low as the DDPG without the controls policy trainer. And so I would like to look at this further in order to learn more about how beneficial it is. So in conclusion, agents can be fairly difficult to train. It's not necessarily an easy task, even though the task may seem simple. A more complex agent doesn't necessarily yield better results. And so you really want to choose the right agent, the right tool for the job. You shouldn't go about developing large architectures or developing really complex learning algorithms. You need to analyze your problem and determine the best agent to use. Finally, in terms of my experiments, the reward prioritized memory is not necessarily beneficial. It probably isn't worth the additional computational cost, though it may be worth looking into a little bit more. But the controls policy trainer I would like to look at further. It might actually be beneficial, and in particular, by copying the policy, we can train several agents at a time with different architectures or different algorithms in order to further improve the controls policy trainer. Thank you so very much for listening, and I hope you had a great day.